Here we go. Are you ready for day number 10? Dilations. Page number 49. Go ahead, give yourself a couple seconds. Dance it out, getting ready. Day 10, dilations. Here we go. All right, day number 10, dilations. First, right off the bat, pause the video if you need to. You are going to need a compass and a straight edge for the end of this topic, all right, because we need to do dilations using your compass and a straight edge. So go ahead, pause it if you need to. I'm going to move on. First, we have a new vocabulary term, invariant points. Here's what invariant points are. Those are points that remain the same after a translation. Okay. So if I have 0.12 and I do a reflection, rotation, dilation, translation, and it remains 1, 2, that point is called invariant. That is called an invariant point. Okay. So a couple examples here of an invariant point. Let me grab a little graph paper here. Visible. Okay, guys, so this quadrilateral right here, I don't want to do a ghetto graph. You guys are better than that. You deserve more. Okay. So it asked me what transformation will result in point B being invariant. So if I graph point B, 0, -3, there's point B. So what type of transformation could I perform that will allow B to stay right where it is at 0, -3? Well, first thing I'm sure comes to your mind is we could do a little reflection around what line. What line could I reflect over that B stays B? And that would be your y-axis. I'm not on my Chromebook today. I'm on my laptop, so I don't have my stylus. Or the stylus doesn't work on here, so I'm using my mouse. So sorry about that. Okay, but what class are you in? Say it loud. What class are you in? That's not going to be good enough. I want another line I could possibly reflect over here. Okay, what line could I possibly reflect over? Well, we just did this vertical line. What about if I reflect over this horizontal line right here? B's not going anywhere. What is the name of that horizontal line? Please dig deep. Well, it's horizontal. So our days together face to face, that was y equals a number. And where does it go through on the y-axis? -3. All right. Now, could we also get fancy here and say, okay, I could do a rotation of 360 and it would be there. Okay, you got me there. Great job. All right, I could do a translation of 0, 0. All right, okay, who brought the cool kid to class today? All right, we don't need any of that stuff. If you do want to get a little bit more creative, we could say a rotation of, you pick the degree, 90 degrees around point B. Okay, so if I rotate anything around point B is going to stay right where it is. Okay. All right. Next up, you guys could probably do these on your own now. What would make point D invariant? So let's get point D graphed, which is 3, 0 right here. There we go. So what could I do here? Okay, I could still reflect, right? But now I could reflect it through the x-axis and it would remain the same. How about a vertical line? I could reflect it through there. Okay, how about a vertical line I could reflect this through? How about this vertical line right here? If I reflect point D through there, it is not going anywhere. The equation for that green line I've just drawn in Well, it's vertical, so it's got to be x equals, and it's going through where on the x-axis? 3. So I could say reflect through 3, or I could rotate any amount of degrees around point D. Okay? So there we go. All right, invariant points. All right, now let's actually talk about today's topic, which is a dilation and what actually is happening during a dilation. So go ahead, take a minute, pause the video, go ahead, graph triangle ABC. All right, so what is actually happening during a dilation? Because I say dilation to you guys and automatically I'm going to get gets bigger, gets smaller. Those are the first two things out of your mouth. That's what happens during, and you're right, that's what happens to a figure, that it gets bigger or smaller. But what actually happens to a point? Like if I just have a point, does that point actually get physically bigger? Let's obviously not. Okay, let's be real here. What happens to it is the following. Okay, you are going to get a number, a dilation here of 2. We have talked about that number in the past. If you guys may or may not remember it from our similarity days, that number right there is called our scale factor. Scale factor. And if you remember, if it was bigger than 1, the figure would increase in size. It would enlarge itself. If that number is between 0 and 1, it would reduce in size. All right, it gets smaller. What it also tells you is if that number is bigger than 1, each point is going to get further away from the origin. So A, B, and C all have a distance from the origin right now. It is going to, in this case, 2 with the scale factor of 2, is going to double that distance away. All right. So the point itself does not get physically bigger, but it will increase its distance away from the origin. Now, if the scale factor is between 0 and 1, now the points wouldn't be getting farther away, it'd be getting closer to the origin. All right, so if the scale factor is bigger than 1, the points get further away from the origin. If it's between 0 and 1, they get closer to the origin. Okay? It is possible to have a negative scale factor. I really don't want to get into what happens then, but it is possible. Okay, so we're going to have to dilate our points first by a scale factor of 2. So how do I perform a dilation? I don't know if you guys did these back in the middle school days, but plain and simple, if you want to do a dilation, you multiply your x and your y coordinate by the scale factor. So our scale factor in part A is 2. So I'm going to multiply every single x and y coordinate by 2. So A prime becomes 2, 4. All I'm doing is multiplying each of them by 2. Next one becomes 8, 4. And the next one becomes 0, 8. Okay? So now we can go ahead and graph it. And now watch. Every point, guys, will become, watch, A prime, 2, 4. 1, 2, 1, 2, 3, 4. There you go. There's A prime, and it just doubled its distance away from the origin. See that? The point doesn't get physically bigger. That's pretty silly to think that, but it's getting further away from the origin. And by getting further away from the origin, that is how the figure becomes larger. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. There is B prime. And C prime, 0, 8. I think we'll go on top here. 1, 2, 3, 4, 5, 6, 7, 8. Yep. See how all our points now are further away from the origin because that scale factor was bigger than 1. And by connecting them now, you'll see, hey, oh, the figure, I don't want that. The figure got a little larger because the points are getting further away. There you go. Perfect. Okay, now let's do the scale factor of 1/2. Read carefully, please. Graph and state the coordinates of A double prime, B double prime, C double prime, the image of ABC. So I'm not going to use the previous coordinates. I'm going back to the original. All right, going back to the original. So here we go, A double prime. Now you're going to multiply everything by 1/2. So we're looking at 0.5, comma 1, B double prime, we are looking at 2, 1. And C double prime, we are looking at 0, 2 now. So go ahead and graph that if you'd like. Pause the video, and you'll see the points are getting closer, so therefore the triangle is getting smaller. All right, so that's what's happening, guys. All right, scale factor bigger than 1, get further away from the origin. Scale factor between 0 and 1, we're getting closer, and that's why a figure would enlarge or reduce itself. All right, so we're good there. Dilations multiply by the scale factor. You're ready to roll. Okay, here is a big part of today and on the Regents exam is how to dilate a line. All right. Now, again, you think about a line, there's no way you can make a line bigger or smaller. What you're doing is you're taking the points on the line and making them further away or closer to the center of dilation, most likely the origin, but it could change like it does in this one. Okay, so I have a line 3x plus 4y equals 20. Determine and state the equation of this new line P after, all right, here we go. After I dilate by 1/3, but now notice here, I'm not dilating around the origin. That's huge. I'm going to dilate it around this point, 4, 2, right? So let's get a look at what this line is going to look like. I got 3x plus 4y equals 20. If I want to graph it, it's got to be in slope-intercept form, which means get y by itself. So 4y equals negative 3x plus 20. Go ahead, divide both sides by 4. Slope-intercept, this is y equals negative 3/4 x plus 5. Okay, so let's get a little peek at what this line I'm going to dilate looks like. So let's graph it. So the y-intercept is 5. So I'll go 1, 2, 3, 4, 5 up on the y-axis. And since the slope is negative 3/4, I can use that to graph a few more points. So down 1, 2, 3 to the right, 1, 2, 3, 4. Up 1, 2, 3 to the right, 1, 2, 3, 4. Let's graph that sucker in. Here is that line. Okay. Now, since we know it's going to be a dilation of 1/3, I cannot, ready for this one, guys? Please listen carefully here. I cannot just multiply these coordinates by 1/3. That rule, that little trick and device only works when I dilate around the origin. That's the only time I can multiply is if I'm dilating around the origin. Here, I'm dilating around a new point, which is 4, 2. Hey, take a little peek. Where's 4, 2? Go ahead. Look where 4, 2 is. 1, 2. 1, 2, 3, 4, 2. Oh, let's talk here, kids. That ended up on the line. So what we're doing here is that we have a 1/3, which means points are getting closer. So here's what we just figured out here. A dilation of 1/3. All right, here's what's going to happen. That means all points on the line will get closer to 4, 2, the point we are dilation is centered around. That's what that means right there. 1/3, because it's between 0 and 1, that means the points are getting closer to something, and that something's 4, 2, which is where we're dilating around. So I want you to think about this right now. All right, let's go back to our line we graphed. Let's take this point right here. That's going to get closer, a third of the way closer to 4, 2, this point right here. Where's it going to end up? I don't know exactly, but I can tell you pretty much it's going to end up still on the line. I'm just getting closer. Where is this point going to end up? If I got to get a third of the way closer, it's going to end up on the line still. All right, let's take this rando point right here. It's going to get closer to 4, 2. All right, it's getting closer. Every point I move, guys, every point I get closer is still going to be on the line. So what am I trying to tell you here? If I dilate with any scale factor, if I dilate, doesn't matter the scale factor, around a point that is already on the line, the image is going to be that same exact line. If you dilate around a point that is on the line, your image will be the same exact line. Okay? Because I'm moving closer or further away from a point that's already on the line, which means the new point, the new image points will still be on the line. Okay, I'm hoping that starts clicking a little bit now. Okay? Well, we are going to get problems where the point's not on the line. It's maybe back to the origin, like this one. All right, so let's see this one. I have 3/2 x minus 4 after a dilation of a scale factor 3/4 centered at the, okay, now we're at the origin. Okay, so let's see what this line looks like again. So -4 on the y-axis, 1, 2, 3, 4. Up 3, 1, 2, 3, to the right 2. Up 1, 2, 3, to the right 2. 1, 2, 3, 2. 1, 2, 3, 2. Okay, still looks good. Graph. Boom. 1, 2, 3, something. I don't know. 1, 2. Okay, man, they're all good. Okay, we see that we're going to center it at the origin. Is the origin on this line? No, it's not. So that means it's not going to be the same line like we had in the previous problem. Okay, so what's happening? Our scale factor is 3/4, which means to me everything is getting closer to 0, 0. All right. And we can do the little device I gave you a couple of problems ago, which is take your scale factor and multiply x and y by it. Okay, so let's do that. Let's take this point right here, which is 0, 4. So multiply 0 and 4 by 3/4. You should get 0. 3/4 times 4 is 3. Here is your dilated point, 0, 3. Closer to the origin, right? Okay, let's try another point. Let's take this point right here, which was what? 1, 2, 3, 4, 2. Okay, multiply both coordinates by 3/4. You should get over 3. 1, 2, 3, up. Let's see, 6/4, 3/2, so 1.5. So up 1.5. There it is. There's that point. Okay. And what you guys are going to know, if I connect these right now, I know they're pretty close here. But what do I see about those two lines? They're parallel. When you dilate a line, it remains parallel, unless it's the same line like in the last problem. But anytime you dilate a line, it remains parallel, which means for the 100th time this year, what do I know about the slopes? Then if the two lines are going to be parallel, the slopes are going to be the same. So when you dilate a line around the origin, it will remain parallel, which means the slopes are the same. And the only thing that's going to change is the y-intercept. Notice 0, 4 went to 0, 3. The slope of this line was 3/2, so it's going to remain 3/2, but now it's just got a different y-intercept, which is -3. Okay, so recap again so we can go quicker through the next couple set of problems. When you dilate a line through the origin, it remains parallel and just has a new y-intercept, which you can find by multiplying the coordinates by the scale factor. All right, here we go. So I got line MN dilated by a scale factor of 2, so that tells me the points are getting further away. Centered at a point 0, 6. Okay, you better be the lights better go on here that it's not the origin, so something's happening here. And MN, this line we're going to dilate, is -3x plus 6, which equation can represent M prime N prime. All right, so because I'm not dilating around the origin, something's going on. I do want to test this a little bit here. Y equals, I don't need to graph it. Y equals -3x plus 6. God, this is awful. Sorry, everyone. I apologize profusely. negative 3x plus 6. How can I test if 0, 6 is actually on that line without graphing? Plug in 0 and 6. So plug in 6 for y and plug in 0 for x. And you'll find out, hey, 6 is equal to 6. That means that point must be on the line. I know some of you are probably saying, well, isn't 0, 6 the y-intercept? And you could tell 6 was the y-intercept from the equation. You can do that way as well. But we just showed right here that this point, 0, 6 is on the line. So what did we say? If it's on the line, the center of dilation is on the line, the image is the same line you started with. So we started with y equals negative 3x plus 6. And that is going to be our final line. Because all the points are getting further away, sure, but they're going to stay on the line. All righty. Next up, Aaliyah, our girl, says that when that line is dilated by a scale factor of 2, at that, oh, hey, again, we're not dilating around the origin. Heads up, that the equation of the dilated line is negative 4/3 x plus 16. Is she correct? I don't know. Well, let's find out. There was the original line. You can try to graph it if you want. That's why I provided the little slice of graph there. So you don't have to draw a ghetto graph. I'm going to test it the same way I did up above. I'm going to say, is 4 times 3 plus 3 times 4, is that equal to 24? Because if it is, that point's on the line and we're in business. Okay, so, what do we see here? 12 plus 12. Yep, that's equal to 24. Check. So that's on the line, which means what, guys? The image will be the same line, 4x plus 3y equals 24. Now, Aaliyah is saying that it should be y equals. Well, she went ahead. She was she's an honor student, all right. She went above and beyond and did it in slope-intercept form. So we need to put ours in slope-intercept form to see if they match. So move the 4x over. And divide by 3. And oh boy, I think we got an issue. Because my y-intercept came out to be 8. Aaliyah's is 16. So I believe we got a little incorrect. So we're just going to write a little, because it does say explain yourself. So we'll just say she's not correct. Equation would be y equals negative 4/3 x plus 8. Okay. So there we go. Hopefully you guys are picking this up now, that if the center of dilation's on the line, it remains the same line. Whew. All right. Oh boy, you're not going to be happy now. So I got the coordinates of AB. There's A, there's B. I am going to dilate by 1/2. So we know what's happening to this line right now. Getting bigger or smaller if I'm dilating by 1/2. Bigger or smaller? Yes, it is getting smaller. Determine the, our favorite, length. Determine the length of A prime, B prime. So we know what's going to get busted out, kids. Oh, it's been so long. Been so long. We've missed you. The distance formula. Stop rolling the eyes. You love it. You just don't want to admit it. Okay. So a couple ways we could do this. All right. There's one of two ways. First way is we could find the distance of AB and cut it in half. Or we could find A prime, B prime right now by multiplying these coordinates by 1/2 and then doing the distance formula. Either way, you're going to have to cut something in half and distance formula, no matter what order you did. So I'll let you guys choose the way you want because I don't want to force a way on you. So pause the video, find the distance between AB, cut it in half, or find the new points A prime, B prime, and then use distance formula. All right, and then we will talk here in a minute. So go ahead, pause the video, try that on your own. I'm going to keep going. Okay, welcome back. You should have found the distance of A prime, B prime to be 2.5. 2.5. You guys that found the distance, I found it by doing the distance AB, which was 5, cut it in half. Even if you found A prime and B prime and did distance, it should still be 2.5. All right, everyone good? Okay, in the home stretch now. Remember, you guys yesterday for me proved triangles congruent by using rigid motions. Well, unfortunately, dilation is not a rigid motion because it changes size. But we can still use dilations to prove triangles not congruent, but similar. So first off, part A, describe the transformation that was performed. Well, obviously we know it's a dilation, right? Well, just like the last 2 days, that word alone is not good enough. A dilation of what? All right, give me a scale factor, please. A dilation of what? So how can I find the scale factor? All right, same way we did in the similar triangles unit. You need to compare the lengths of two corresponding sides. So for instance, BC is 1, 2, 3, 4, 5, 6 units long. And B prime, C prime, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 units long. I can find the scale factor by comparing two corresponding sides. Now, should I be going 6 over 15 or should I be going 15 over 16? Two different ratios, but only one's correct. Well, let me ask you guys, is ABC getting bigger or smaller? It's getting bigger. So my scale factor has to be, boom, bigger than 1. All right, so I can go back up and say, finish my sentence up there and say a dilation with a scale factor of, you can write 15 over 6. If you want to reduce it, that's what I did, a scale factor of 5/2, but 15 over 6 would have been fine. Okay. Now explain why A prime, B prime is similar to triangle ABC. Well, it's not a rigid motion, so I'm not even going to go into that territory and bring up those words. It does change distance, but it does not. A dilation does not change angle measure, only distance. So what I'm going to write here is something, no pun intended, similar to what I had you guys write yesterday for those proofs. A dilation, I'm not going to say it's a rigid motion, that's false, but I am going to say it preserves angle measure. So triangle, and you guys can write this now. So triangle ABC is similar. Oh, make sure you write the similar sign, not the congruent symbol. To triangle A prime, B prime, C prime. That is awful. Jeez. Okay. So again, we can use dilations not to prove triangles congruent, but to prove them similar because their angle measurements stay the same. All right. Get out that compass and straight edge time. Here we go. All right. So I need a new triangle, A prime, R prime, T prime. Art, very good. Some of you thinking that in your head. Good. We can read. Excellent. By a scale factor of 1/2 centered at 0. So let's just talk about what's going to happen. Are A, R, and T going to get further away or closer to O? The scale factor is 1/2, so that tells me from today they're going to get closer together. They're going to get closer to O instead of being further away. All right, how close? Half the distance they are now. So let's start with point A. Point A, line up your straight edge, has a certain length to O. I want to shorten that distance using my compass by 1/2. Let me say that again, guys. By 1/2. 1/2. Do we know how to cut this line in half? You're darn right. That's our fish. Put your compass point on one of the endpoints. Open it up more than halfway. Let's rock and roll. Swing it. Go over the other endpoint. Swing it again. Line up your straight edge. Now, you don't, and I think this is just going to make it more messy for you. You don't have to draw that full thing in. All right, it's not needed. All you need is to line up your straight edge and mark where that your straight edge crosses OA. There it is right there. And now there's A prime. Take a look, guys. It is halfway closer to O than A was. Okay, so we can now label that as A prime. Okay, and now let's do it for R and let's do it for T. Okay, so go ahead and I'll do it. I'll work with you guys as you do it by yourself. And hopefully we get a triangle that is smaller than the original, right? Because we're getting closer. Again, just to remind you guys, as you prepare for Friday's test, these constructions are all up on Aspen under the transformations folder because we have done quite a few of them. All right, quite a few. And I really don't want you guys looking back at them while you're trying to take the test. I want to see if you can do them all by yourself, like big boy and big girls. All right. I am going to just draw the full line in because I don't have the luxury of a straight edge. Mark that point. And there's R prime. Oh, T is going to be a close one, huh? Going to be a close one. A lot of arc marks. I wanted that in a different color. Flip it over. There it is. Draw my line through so I know where it's going to hit. Right there. Whew. All right. So let's connect this finally. So there it is, a smaller triangle getting closer to O. Okay. Now you can put your compass and your straight edge down. I do want to do something else here, and that is what happens if it's getting further away. Okay, so just let me talk real quick about that, guys. All I need you to do is focus in here. So let me change that 1/2 now to a 2. Okay, so now it's a 2, so it's getting further away. Now, this is not a reflection, so it shouldn't be over here somewhere. All right, my new points. It should be further away. So how would I accomplish this? Pretty easy. So let's say I was going to take T and dilate it by a scale factor of 2. I would draw through it now because I'm getting further away. And all I'm going to do is measure the distance from O to T and copy that distance on the other side. So there's where T prime would be now. Okay, so just a heads up, who knows where it may come up. I think it may come up on the assignment you're about to do. Right, so again, don't reflect it over here. Okay, it shouldn't come up anywhere over here. It should be away from it on the same side of O. Okay, as they get further away. Okay, good luck on the assignment. We'll talk at your next Google Meet, and email me if you have any questions in the meantime.
Music, oh my God.